let's introduce centripetal acceleration. So when you are studying acceleration in general, so you know that you have your equation, which is acceleration is basically defined as the change in velocity that you have divided by the change in time. And the two concepts that you studied originally were simply with regards to speeding up and then slowing down. So really, you were moving in kind of one dimension. So that's speeding up and slowing down. I can refer you back to that definition of acceleration. Now, there's one additional item that can happen, right? We're not always just speeding up and slowing down, because we would technically not really get anywhere unless, it's right in a straight line as we're going. So at some point, if we want to get somewhere, we're going to have to make a turn of some kind in order to get there. And we're not just necessarily just turning with regards to getting to somewhere, but if I wanted to, get off this chair, and I wanted to twist around, well, as you can see there, so I'm basically turning. So when you are turning, then this particular change in velocity does have an impact. And you can actually be going at a constant speed. Yet, if you're changing your direction, then you are going to be experiencing an acceleration. So that change in direction of any kind in the introduction, in terms of when you're just starting off your physics, the assumption is that you will have your velocity that you're moving at, or at least your speed. I'm going to call it V for speed. And that is constant. And then the only thing that is changing is your direction. So aside from the viewpoint of just speeding up and slowing down, we can now introduce and say, okay, well, you can also change direction. And when you are changing direction, then what you are referring to is centripetal acceleration. The word centripetal just means center seeking. So centripetal acceleration is something that we can certainly figure out when we are changing our directions. So what do we mean by that? Well, it turns out that our acceleration, at least the magnitude of it, and I'm going to start writing A and a little c here, we can still put that it is a vector, and I'll explain that in just a moment. But the magnitude of it is just simply whatever speed that you are moving at, you're going to square it, and then you're going to divide by r. Now, what the heck is this r? Well, it turns out that it is the radius that you would create if you continued to change direction at the same constant pace. So, for example, if you're going to be moving along and then you change direction, so as you're kind of moving along in this way, so now you're changing directions. And what you will have, so let me rewrite it, so as you were kind of continuing on, you would have created, this idea of a circle, right? So you would have this particular circle, that would have been your actual definition if you continued on. So it creates this circular path that you have. Now, of course, we're not just going in circles, but anytime you do change direction, so initially maybe you were moving in this direction, but then, a little bit later, so you're basically just switching around, and you're moving along, and this, is going to be perpendicular to that. And you can calculate what that acceleration is. Now, this acceleration that we have, so this centripetal acceleration, whenever you're making a turn, we do assume that this speed is constant. So we're not really changing it because it would complicate our calculations. And initially, when you're introduced to this, actually, for more often than not, you assume that it is constant. And that particular direction is going to be inward. So it is inward. It's kind of towards the center of the circle that you have. Now, why is it inward? And actually, why is it equal to this? So that's a great question. And I'll put up a link up above there because I do show it. But I don't want to show it in this video. In this video, I just want to introduce you to this concept. So the concept is simple. You can change, your motion by either speeding up, slowing down. So those you know relatively well. But now we can add a third one, and that is changing direction. And when you change direction, then the direction that you are heading in, so as you kind of change it, you can create, almost, okay, if you would continue on, a circular path, okay, that would have been at the angle that you're actually just trying to change your direction along. So this does have various application. The formula for it is not very hard, so that is the formula itself. The direction is into the center, okay, so into the center, okay, so hence center seeking or centripetal, so that's what we typically call it. So that direction typically is dropped, and then what you will see is, the vector itself will be dropped, and then there will be really no mention of this because anyone who's talking about centripetal acceleration knows that it is towards the center, right? So now, how do we calculate it and where does it come up? Well, it comes up in a few examples. So let's try to use this particular formula for us, and you'll see that it's not very difficult, yet it has, some pretty interesting applications. So what I've just done before starting off this video, I kind of went on, artificial intelligence, I went on ChatGPT and I said, well, can you give me 2 examples with centripetal acceleration, that I would want to be able to solve, and maybe throw in, a healthcare flavor into it, and this is what it generated for me. So these are 2 nice examples. Let's take a look and see how we can break these examples down and solve them, okay, by using the equation itself. So for example number 1, so it says an arterial stent is inserted into an artery, okay, so an artery, okay, is within, so this is within the human body, okay. If you don't know what an artery is, you can certainly look it up. I would encourage you to do so. So this is very applicable, and it says that it has a diameter of 5 millimeters, all right, so that's right there. Okay, so this is what we have. So diameter of 5 millimeters, which means the radius is going to be 2.5. All right, so I'm going to just start writing down this information because if it's related to centripetal acceleration, I'm going to be able to solve it. So the diameter, or the radius in this case, is going to be 5 millimeters divided by 2 because the diameter is twice as big. So this is really going to be 2.5 millimeters that I have. Now, blood flows through the stent with a linear velocity of 0.4 meters per second. So notice this is my velocity that I have, 0.4, let's say meters per second that I have there. Calculate the centripetal acceleration experienced by the blood as it flows through the stent. Okay, and it actually gives us that the radius is half. So this is a nice little example in here. So what we would do is we would say, well, we know that centripetal acceleration is the speed that we have, okay, so in this case, and it is divided by the radius. Now, we do have to be careful because of the fact that we have to make sure that the units align. So this one is in standard SI units, so it's meters per second, but this one is not. So 2.5 millimeters we would have to convert, right? So you would have to convert it back into meters. So now this will go back and, kind of let you think about prefixes. You can put up a link up above there if you forgot about prefixes in general. So now, 2.5 millimeters, well, what is that equal to? So you can certainly change this up, okay? And I'm going to change this back into meters. So milli, so well, there's 1,000 millimeters, okay, in 1 meter. Okay, so therefore, this is going to be equal to, so I can take this in, I'm going to actually write it right there already. So this is going to be, we're going to shift the decimal over. So 0.00, okay, and 25 meters. So now we can take this, substitute it back in. So 0.4, okay, it is going to be squared, and this is going to be divided by 0.0025. And it's going to be 64 meters per second squared. Right? So I'm going to leave this. I'm not going to necessarily round it to anything, but if we had to round, we could, okay, if this was not sufficient. So there you have it. Now, where is it? Well, this is actually towards the center. Now, what is the center, right, okay, of that? Well, it is within your artery, and you kind of will know that within here, okay, if that is the magnitude of the centripetal acceleration. Okay, so that's one example. Now here's another example, okay, that it has. So another, it looks like healthcare example. So this is an MRI machine. So you maybe have heard of X-ray machines and ultrasounds. Well, MRI is another machine. So it's a magnetic resonance imaging machine. It's one of the better ones. and it typically has very long wait times unless you've got a lot of money that you can take a look, okay, and get yourself all checked out. In any case, so here we have an MRI machine. It's cylindrical in shape, so it does indeed have a cylindrical in shape with a radius of 1.5 meters. The outer edge of the MRI machine rotates at a constant linear velocity of 3 meters per second. Calculate the centripetal acceleration experienced by a point on the outer edge of the MRI machine. Okay, so well, this is number 2. So, well, what do we have given? In this case, well, we have definitely the radius, which is 1.5 meters. So this one is going to be easier. We have no conversions. This is already in standard units. We have our speed. Well, that particular speed is 3 meters per second. So again, both of these are in the units that I want. So I can find out my acceleration. So my centripetal acceleration that I would have. Okay, so this is what the object, the little point, would experience on the outer edge. So if I substitute all of this in, so this is going to be 3 squared divided by this, and there we have it. So this is going to be 3 squared divided by 1.5, and we have 6 meters per second squared, okay, into the center, right? So whatever that MRI machine, so typically it kind of looks kind of like this, right? And then you're slid in here, okay, within there. So, you might be, slid in like this, so this is the person itself, okay, maybe so they're going right in here, okay, and then this is rotating around. So you have an MRI machine, so it's referring to a little point that maybe it's kind of scanning in, okay, and doing our magnetic resonance imaging, okay, on it. So these are 2 nice examples that you have that have been provided, okay, so thank you ChatGPT, so you can take a look. I'm actually going to post this video on the day of making it, so that's when this was asked. So that's pretty neat, and if you always want more questions, you can certainly find them all over the internet now more and more, okay, with regards to this. So that is the introduction to centripetal acceleration. The formula is rather simple. Make sure that your units are all consistent and aligning, okay, and then always keep in mind that the actual direction is always towards the center. So it is right there. That's where your centripetal acceleration would be pointing, towards the center of the circle. So no matter where you are at, it's always going to point inwards, okay, as you are moving around. All right. Thanks for watching. We'll see you in a future video. Bye, everybody.